Hello, my name is Ömer, a fresh PhD graduate from Manchester. In this video, I'm going to briefly talk about my PhD research. I performed my project as part of EPSRC MIDAS grant, which aims to develop mechanistic understanding of irradiation damage in zirconium alloys used in most nuclear reactors. I particularly focused on the irradiation-induced microstructural and mechanical evolution in three commercial alloys, namely zircaloy 2, zircaloy 4, and Lawton-Zerlo. While MIDAS grant has access to valuable neutron-irradiated Bohr-60 materials, I used proton radiations as a surrogate to emulate the neutron damage behaviors to address specifically the low-dose regimes where it has usually been overlooked. During my project, we carried out several proton radiation experiments to range of doses from very low dose regimes, including differing dose rate irradiations, to explore this effect. The resulting damaged structures were investigated using the state-of-the-art machines including STEM, PFIP with cryostage, APT, nanoindentation, and novel microbeam transmission synchrotron XRD technique. All the irradiated material characterizations during my project were carried out from the cross-section of the samples where the entire proton radiation depth-dependent dose profile can be investigated. While the investigated dose rate difference did not produce any significant changes in zircaloy 2 through synchrotron XRD dislocation density measurements, it was found that the highest irradiation dose rate to produce comparably higher dislocation density in Lawton-Zerlo. However, latter alloy was found to have this drastically smaller dislocation density compared to zircaloy 2 in each dose rate conditions after 0.15 dPa nominal proton irradiation damage. Moreover, almost immediate niobium nanocluster formation was confirmed through APT experiments in Lawton-Zerlo, while dose rate increase seemed to result in smaller cluster size. The STEM investigations of the two alloys revealed significant A-loop alignment along the basal planes at this early damage level, while this was less pronounced in Lawton-Zerlo samples. Investigation of the proton radiation depth-dependent dose behavior with the spatially resolved XRD and nanoindentation techniques showed that while dislocation density increases significantly, hardening does not follow the same trend and was found to saturate early on. This is explained using simple dispersed barrier hardening model by introducing XRD-generated outer cutoff radius variable. This suggests that at higher dPa levels, the density of smaller dislocation loops give rise to higher overall dislocation density, while their strengthening effect is very small. Lastly, proton radiation depth-dependent damage behavior was once again exploited to compare the dislocation density measurements from XRD and STEM. This was achieved by utilizing our PFIP microscope with its cryostage temperature capability. Large FIP foils in the range between 40 to 50 microns were prepared to image the entire proton radiated region on the same samples and on the same surfaces where the XRD measurements were carried out. The results show good agreement between the XRD and STEM dislocation density with some discrepancy, especially towards higher dPa levels, which is explained by the presence of small dislocation loops that go unnoticed in STEM imaging. Thank you very much and hope to meet you in future nuclear material projects.